So my name is Vitaly, and I'm going to be talking a little bit about the swapping in Linux kernel, and particularly swapping backends for Zswap, and how it all goes with the latest fashion of doing things in kernel with Rust. And so there will be a presentation on the Zswap backend written in Rust and how it compares to basically the same thing written in C and the other existing backend called Zsmalloc. A few words about myself. So I've been doing embedded Linux for many years, starting from Mona Vista Software. So that's a well-known company in a tight posse. So I don't know if you've heard about it, but that was one of the pioneering companies in the embedded Linux field. Moved to Sweden in 2009 and worked for Sony Ericsson, Sony Mobile. That was a big cash basin for the consultants from all over the world, basically. And I'm now still living in Sweden, but in Malmo, and I'm running a small consultancy company called Consulco AB, which is a part of the bigger company from the US called Consulco Group, Consulco Inc. And it's founded pretty much by the same guys I was working with down in Mona Vista time. So we sort of keep that inner posse. In this presentation, as I said, I'm going to be talking about the swapping in general, just to give a background, and what is the Zblock, this new backend that we were developing, and how it all came to trying the rustifying the existing C code, and why, and how it all went, and what obstacles we as C engineers came into when we were doing the Rust thing. And we'll do some comparisons. That's the fun part. I'll show some steps that we did profiling and improving the performance of the Rust version, and we'll do some comparisons again and see some graphs and stuff. And I hope that will be rather fast, and we'll have quite some time for questions. So let's begin. So swapping. I mean, I always carry this slide in all the presentations of the kind, and usually I just go through it very quickly because everyone knows what swapping is. So it's just using secondary storage for the data that the system is not using currently, because RAM is an expensive resource and we want to save it for something that we really want to use right now or in the closest future. So we just push out the pages of data that we don't use at the time. And where we push it to some secondary storage, which is usually a flash device or solid state disk or an ordinary hard disk or whatever. And of course, the secondary storage will be slower, less performant than RAM in pretty much all the cases. So we can say that we trade memory for performance. And in some cases, especially for embedded applications or for applications somewhat sensible to some real-time characteristics where we want reaction, like soft real-time. I don't speak hard real-time, but still. We want reaction. In this case, or in some cases of the kind, it will not be exactly acceptable to have long delays that could be caused by getting the pages back from the secondary storage, which is slow. So in that case, we want to do something to mitigate the problem, and that is to use RAM to cache swapped out pages, which is kind of counterintuitive because we were saving RAM by pushing the pages out, and now we're trying to use this very RAM to store these pages for some reason, but the thing is that since these pages are officially not used by the kernel at the time, we can compress them and save the space by compressing the pages which were to be swapped, but we took a pause, you can say, and saved them in the compressed state in RAM, and thus we do save space, and at the same time it's still faster to retrieve them if we want them. So we trade back performance for memory, but then again we gain more flexibility in what exactly we want to achieve in terms of the RAM and performance trade-off. So, and how do we do that? The primary means is Zswap, if we speak about the kernel, the Linux kernel, which is compressing swapped out pages and moving them into a pool. And when the pool is full enough, well, you know, rest of the pages will obviously go all the way down to the secondary storage. But usually it's not happening that often. So what we have is we have the infrastructure to intercept pages that are on the way out, compress them, and store somehow in memory, and then we need an effective means of storage, an effective allocator, and in that sense the ordinary kernel allocators are not exactly a good match, so we need some kind of a specific allocator that is capable of densely arranging smaller objects, because we are compressing on a per page basis, so if we do good, the objects may be very small, but all the way to the page size, because if the compressed object is larger than the page size, then it makes no sense to store it that way. We will store it uncompressed. So it's an allocator that should be capable of storing smaller objects in a dense way. And there were 3 such allocators up until recently, all using Zpool API to communicate to Zswap, to provide callbacks to Zswap. And now there's only one, ZSmalloc, which is very fair, because it's one of the fastest and definitely the best in terms of the compression density. So now it's only one, but on the other hand, it's rather big, because there's a lot of functionality in there, and a lot of stuff to maintain the high compression ratio and to fight the fragmentation that occurs over time. We will not be really diving too deeply into this. Let's just say that ZSmalloc is now the only one remaining in the kernel, and what we will be talking about is an alternative to it, which emerged from the work that we've been doing for a different project. And this is the slide about the callback interface for Zpool API. Is done for reference. We may want to return to it. At this point, it just doesn't make any sense. So we'll just go through it. And we'll pass over to Zblock, which is an alternative to ZSmalloc, which turns to be faster and basically on par or almost on par with ZSmalloc in terms of the compression density. And it is based on the 2 simple ideas. Well, the first idea being that with the recent advancements in the kernel memory allocation, especially in the vmalloc vmap interface, we don't need to reinvent the wheel and do some very complex allocations that ZSmalloc is doing. And the second idea is that if we divide large blocks into array of same size objects, which pretty much every such allocator is doing, then these objects, they really don't have to be of a power of 2 size, because it's just not optimal. So let me go here. So as an example, let's allocate a block of 2 pages, which will be 8K bytes, 8,192. And then there is a header, which resides in the beginning of this block. So we have 8,144 bytes remaining. And then we can, for instance, just in case, we can divide the remaining block into 11 subblocks of size 740 bytes, which is like an odd size. But on the other hand, if you compress objects, they will have odd sizes as well. So we have 11 chunks or 11 sub-objects of these 740 bytes. And then we have a small remainder, which is like 4 bytes only. So you can hardly see that on the diagram, but here it is. Oops, sorry. Where is it? Here it is. So this is the 4 bytes. So we don't care about this 4 bytes because it's negligible. And then if we can come up with the numbers that are good enough to divide these large blocks into, then we can be quite on the good side with storing these compressed objects that come from ZSTD or LZ4 or whatever else compressor there is. And at the same time, there will be no objects spanning across the blocks. So we will always deal with one block at one time, which is very important because in this case we don't really get the fragmentation that ZSmalloc is having. On a high level, Zblock, what does it do? It finds an appropriate block type to fit the object of a certain size that we are about to store. And then we mostly fiddle with the first block of each type because by the implementation, by algorithm, we guarantee that the first block of each type should, in the list, we have a list of the blocks, should have at least one free slot. So we just take this free slot. And if there are no more free slots, then we take this block off the list. And if there are no such blocks in the list, if the list is empty, then okay, we need to allocate one. Well, freeing is kind of intuitive. And since we really want to go into the Rust thing, I will not really take too much time discussing that block operation, unless someone wants me to have this in more detail. But I guess no. Let's do a vote. Who wants to who wants a quicker pass over to the Rust section? Okay. Who wants more details on Zblock? It gets complicated because it's roughly 50-50. Okay. Yeah, we'll do something in between. I hope I will not exceed my time. So for freeing is simple. So there is a handle. That's the part of the API. You get a handle of the object that you're freeing, and if we get this handle, we can find the slot corresponding to the handle, and we mark the slot as free. And if all the slots in the block are free, then we free the whole block. On the other hand, it's not written here, but also if this is the first free slot in the block, if all the slots were occupied, then it should be returned back into the list. Okay, so quick comparison. As I said, Zblock and Z3-fold are all history, so they have been obsoleted and taken off of the mainline kernel. But just to give you a perspective of where we are with Zblock in terms of the compression and performance, we can see that the two obsolete backends, Zblock and Z3-fold, are worse in compression, and well, Zblock is basically on power and performance. And if we take the only existing ones at Zmalloc, then Zblock is slightly worse compression-wise and slightly better performance-wise. So that's where we are right now. Okay, so let's go to Rust. Where does the whole thing come from, right? So, I mean, we have a C implementation, and it's kind of working. Why do we need to go to Rust? So the story is, well, we are a consultancy firm, and we are sort of customer-driven, with a commitment to the Linux community, of course. So we had a customer asking at some point if we could have a memory-safe backend for Zswap. Like, what do you mean, guys? Well, we thought you could rewrite the Zsmalloc in Rust. Now, God forbid, we can't do that. Now, we can do that. We did an estimation. They didn't like the estimation. So it was kind of in a deadlock. But then I had an idea that it would be easier for us to rewrite Zblock in Rust because, first of all, we did implement it. So we have like a deeper knowledge of what it actually does. And the second thing, which is maybe even more important, is that it's actually simpler. Zsmalloc is, I mean, that's a huge pile of code written by many people, and Zblock is like 5 times smaller when it comes to the code size. I mean, source code size. So we said, well, you know, we're going to make a prototype and we'll see how it goes. And if you like it, we'll do the rest of the work, because we were also interested in trying Rust. And so there was this initiative to rewrite Zblock, this new allocator backend, into Rust and see how it compares with Zsmalloc in the first place and the C version of itself in the second. Yeah, so I really want to say that it's a good picture. I really want to say that what I'm trying to, the message I'm trying to deliver comes from a person who was a C developer for like 20 plus years. So people coming from a different background, like learning Rust from the beginning, can have a very different opinion on this. But for me, and not only for me, it was a very bumpy road to actually start building, not even writing the code, but start building the Rust parts in the Linux kernel. That wasn't really easy because, you know, the first thing I did, I installed the Rust compiler on the Ubuntu workstation, and then I figured out that it wasn't the version that I could use with this Linux kernel revision. And if I want to do like things on the bleeding edge, like on the Linux Next or MM Next or whatnot, the latest kernel from Torvalds or the latest kernel from Andrew Morton, then I need yet another version of Rust compiler. And so we had this production kernel that we were working on, and we had like the upstream version that we were also working on, and we had two different Rust compilers, none of which was the compiler that was installed in Ubuntu by default. So that wasn't really reassuring. And then again, on x86, x86-64, we actually need the whole CLang suite to be able to compile Rust. So it's dependent on LLVM in the first place. And on ARM64, it turned out it wasn't. So we were compiling Rust with cross GCC on ARM64, and we were getting not exactly the same results we would get with CLang. And so part of the testing that we had done at some point wasn't really applicable, and it all sounds like tiny problems, but in the end we spent quite a bit of time doing wrong things instead of doing right things, and that sort of contributed to a bit of frustration.
Question.
Yeah, sure.
Did you make sure to patch the documentation we appreciate it. When you find something that's doesn't work or is not correct, please send a patch.
Yeah, we will. Actually, this is like a thing of the past. So now I think the documentation is quite okay, and the Rust compiler is actually more stable. So I don't think if you start from scratch now, you will probably not hit all the bumps that we hit. But in the end of the day, we do want to go from the very beginning to the very end and compare that with the things that are written in documentation Rust to see if there's anything missing. So that's in the plan. Yeah. Okay, so when we got the things compiling, what's out there that we need to consider? How do we Rustify the existing code or the existing algorithms in the right way? It doesn't really work to try converting the C code into Rust code. We need to decompose it again in a sense of used algorithms and data structures, and try to recompose it in the Rust way, because using C paradigms doesn't seem to work. The languages are too different. And that was one of the things that we discovered. And the other thing was that the integration, if we are doing some core things in Rust, then we need to do the integration of these core things into the APIs that are written in C, and we need to call functions defined in C code, and we need to pass structures to C functions, and there are means in Rust to do that, and we did it in this very straightforward way in the beginning. So we just mirrored the structures, and whatever was there that wasn't defined yet, we just mirrored directly in the Zblock Rust implementation. And of course, it wasn't right, because by doing that, we limited our ability to leverage the stronger sides of Rust. At some point, we went back and created bindings for Zpool, because this is the primary API that we were using. So we created the trait for that pool and the trait for registration, and there's a snippet of how it's done in the implementation of the registration trait. So we call register function from Zblock Rust, and it does register the things in the C way. And by doing that, we first of all we open up to having other backends in Rust should they appear, or I don't know, ZSmalloc re-implementation should it be actual. And the second thing is that for us specifically, for Zblock Rust specifically, we gain more flexibility to use the stronger side of Rust with the memory safety, in a limited way at least, and using the Rust idioms and allowing the Rust compiler to understand better what we do and to optimize things for us. Algorithms. Well, we don't do any rocket science in Zblock. So what we have there is the bit search, because the empty and occupied slots are represented by a bit array. So we do bit search for an empty slot. The search for the block type corresponding to the size of the object that we need to store is implemented using the red-black trees. So arbitrary search, it's implemented in the C part of the kernel. Luckily, it's implemented in the Rust side also. And then we have double linked list manipulations, which pretty much every Linux driver does in some way. And yes, we needed to look what Rust kernel infrastructure has to offer with regard to the things that we needed. And yeah, we were unpleasantly surprised in part of it, and in another part it was just okay, but let's go into more detail. So linked lists. I'm going to read this. I do believe that having struct linked list head in the kernel is one of the best things that have ever happened in the kernel. This is an awesome idea because you have the pointers now which point to the previous and to the next, and every entry can be ahead of the list, so it's all symmetrical. And for storing or adding or removing an entry from the list, you don't really have to allocate anything. So actually, this is a great thing, and the kernel is benefiting tremendously from it. The linked list implementation in Rust is reasonable but somewhat complicated because of the whole idea of having to be memory safe and even I think they claim that it's thread safe. I'm not sure about that, but whatever. And what we do in Zblock is, first of all, we use the first element. The rest of the stuff there is just for the record, basically. So we use the first element, and sometimes we delete it. So that sounds more like a stack, right? So we had a huge temptation of trying to use a stack-like structure, and there is some like kvac or vvac. There is such a thing in Rust, and we tried to use it. And yeah, we'll go back to this. I thought I had a slide showing that it didn't really work, but we'll get back to this. So we wanted to use vectors We tried, we didn't succeed, and later I show why. Red-black trees in the Rust part of the kernel are working just fine. We didn't have any problem with that, so that's just okay. Nice to use thing. Rust and memory allocation. Well, writing a memory allocation driver, a backend in Rust is somewhat challenging because Rust is designed to be memory safe, but it can't be. This implementation can be memory safe because we are allocating and freeing memory on our own, because that's basically the purpose of what we do. If we're implementing bits of memory management in kernel in Rust, it just can't be memory safe. We need to allocate pages directly, and we did have to use the C API, but the thing to look after here is to try minimize the amount of marked unsafe blocks in Rust. So we can do that. We can use unsafe, but there always is a temptation to put too much stuff into unsafe block and just forget about it. So that's not exactly right. We need to leverage the Rust capabilities of finding weird stuff for us. But on the other hand, we cannot completely rely on Rust because there will be unsafe operations if we are doing memory allocation ourselves. And this is what we do because this is the nature of the work that's been done. The worst thing that we came across while looking into the Rust analogs of what we use in the C version of Zblock is the Rust spin locks. The Rust spin locks are implemented more or less like monitors, so you sort of don't have to care about releasing a spin lock. But you know, this is kernel programming. So if you're a kernel developer, you probably should be able to call spin lock unlock, right? So this is an overkill. I understand where these guys were coming from, but this is an overkill. Yeah. I know. But then again, the whole idea of having a guard, which is effectively a monitor, right? The whole idea is a bit. I mean, it doesn't really go that well with the spin lock idea as such. So a spin lock is effectively a mutex which does the mutual exclusion by spinning and disabling preemption. So the idea of the mechanism is to have a clear lock and unlock, and whatever is in between, we sort of know that it's safe. And this works differently. So there's no direct mapping to any mechanism in Rust implemented in the kernel. There's no direct mapping of spin locks, and this is something that we wanted because there were structures that we didn't want to use guards for. We want to have some more fine-grained spin locking and unlocking, and this wasn't possible except for using the C spin lock directly via bindings, which is in turn unsafe, but it does increase the performance. Okay, comparisons. So what we were pleasantly surprised with was that the size of the objects compiled in Rust from Rust was roughly the same as the ones that we had compiled from C code. So if we do stripping, it's even more so. So the Rust compiler is doing a good thing. I mean, doing a good job. And then we did some performance comparisons as well. And at that point, the first implementation, the Rust implementation was losing both to ZSmalloc and to Zblock, not by a huge margin, but it was losing on all targets that we used. It was like reference ARM64 target, Raspberry Pi 5, and there was a QEMU virtual machine taking 12 cores out of 24, I think, on a Ryzen. And yeah, I mean, don't be fooled by the difference here. It's not a huge difference because it starts with 440. So it's not marginal. The difference is not marginal, but it's not as huge as you can think of by looking at this chart. And then it's interesting. Oops, sorry about that. It's interesting actually that if we use the number of threads, heavily loading CPUs, heavily loading the cores, that divides well by the number of cores, then the difference is bigger than if we use some odd number of threads in the make. So that's an interesting observation, but we didn't really figure out that much why. But it's something to look into, maybe for some further optimizations.
What's the unit on the x-axis?
Seconds, right? So it has. So it's the amount of seconds to build a BZ image on that machine. Okay, so at this point, what do we have? We have Zblock that is slightly faster than ZSmalloc, but we knew that. We have Zblock Rust that is slightly slower than the both of two. And then we had some questions like, why is that happening? Why is it so? Is it, some Rust suboptimality, or is it like we mapped the structures in a not so good way, or something else? So we did some profiling, and yeah, that's here for a purpose. When I am, as a C developer, I'm used to having nice obj dumps that I can easily comprehend, and that is not the case for Rust, because it has these complex names all over the place in the object files. Now it's kind of.
You could just add numbers to perf, like this one.
Okay. Yeah. Life isn't. Life goes on. That's good. That's good. It's good to have to see the progress in tools as well. And anyway, I was a bit frustrated, but on the other hand, like life is life. So we used perf and ftrace to profile these implementations. And well, we knew from the past that Zblock spends a lot of time on allocation, and this is where we need to optimize things. And for Zblock Rust, it was true as well. And the problem, one of the problems was this is the story about the vectors. Vectors seem to be nice, but if you grow it, I mean, if you use it as a stack and if you grow it, then there will be a reallocation, and these reallocations don't seem to be very optimized in the existing implementation of KVAC in Rust. So one of the things that we had to do was to go back to linked lists. Oops. Okay, I'm running out of time. That's good. Thank you. Thank you, my iPhone. Thank you. So we needed to go back to linked lists, and that actually turned out to be working fairly well. And another thing that, I was criticizing Rust quite a bit before, but the good thing that we got from Rust, and that we had good hints from Rust in runtime, like this one, which came as a surprise, and then we saw that there was a ref counting thing happening because Rust was keeping track of the objects that we were manipulating. But actually, we didn't want for Rust to keep track of objects we were manipulating with, because we wanted to free them ourselves, because we did allocate them. And that was another thing that we needed to fix. And it really looks like kind of weird. So we do a seemingly useless operation like this one, but it's not exactly useless, because it actually tells Rust that it shouldn't care about this object anymore, and then it works. But we do need to create some documentation for this, because it will be really cumbersome to figure what exactly this thing is supposed to do in half a year. So even me, if I take a look at this code in half a year, I'm pretty sure I won't be able to tell what it's doing. Finally, spin locks and RCU. Let's make the long story short. RCU is not really implemented in the Rust part of the kernel, and that is kind of unfortunate, because if it were, we would have used it. So we had spin locks. We kept the spin locks via bindings, and then there are some helper routines in C to manipulate the bit arrays, and we had to re-implement that in Rust and do profiling as well, because that's one of the basic searches that is on the hot path. And it turned out to be pretty okay. And also a good thing that this match operator in Rust is pretty powerful, and it is optimizing things by quite a bit, and using it instead of doing multiple ifs or if else. However simple it seems, it actually does make a difference performance-wise. At the end of the day, what we have, we really didn't expect that. But what we have now is that the optimized Rust version of Zblock is operating faster. Not only that the non-optimized version of Zblock Rust, but also it's faster than the C version. And it really came as a surprise, but this is what we have, and it puts things in a different perspective, at least for me as a C developer, because I was inherently sure that C is superior anyway. Like we have Rust, which has these advantages, but C is superior anyway, and the testing showed that it actually wasn't really exactly like that. So that was really unexpected, but also it's truly remarkable that Rust can achieve this performance. And out of the Rust versus C stereotypes, there are several that didn't stand, and they're mostly negative that didn't stand. Like C compiler would produce smaller object files, or C code would always be faster than analogous Rust code. Some of the stereotypes are still true, but maybe they will change. Like Rust and kernel is not beginner friendly. The threshold is kind of high to be able to dive into this and go full speed. And Rust compiler, well, it does a job pretty well, but sometimes you really need to fool it to do the thing you want to do. And it might be a little frustrating. But things are moving forward. And it's absolutely, I'm absolutely sure that Rust is now a first-class citizen in the Linux kernel. And we have a living proof that it's possible to implement core subsystems in Rust. And these parts, these implementations, that they will show high performance. And even though there are still many things to be done in the Rust kernel field, some of which we have stumbled upon, I'm pretty sure that we'll see Rust C code ratio increasing over time. So there will be more Rust, and we need to get prepared to this if we're not yet. And that's probably the main outcome of this presentation. Sorry for taking so much time. Thanks for attention. I hope there's still some time for questions.
Yeah, well, we'll welcome Yanis on stage. Yeah, so Yanis, could you?
I was wondering, you mentioned using bindgen to generate C or Rust from C to start with, but you decided not to use it. Did you consider using C to Rust to create unsafe Rust to start from that instead of starting from scratch?
No, we didn't.
Any particular reason?
Well, no valid reason, I would say. But there is an invalid reason, and the invalid reason is that we were so afraid of that whole code generation thing after spending a lot of time making bindgen do the thing we wanted. That we decided, well, we're not going to mess with the code generation at this point. We'll just write it from scratch with our own hands. So once again, it's not a valid reason because we didn't really try that, but we were kind of on our toes to just start writing actual code and testing it, and not spending time on fighting yet another code generation thing. So. That's basically how it is.
Okay, thank you. Just for context, how big is the code base?
It's I think it's around 15K.
Yeah,
thank you.
Okay, well, a short one if it's possible.
One very short comment about the comparison you did with object files. Use Zblock or meter tool. It will show you even better results, I believe, because it compares text, not whatever reserved there. And the question is about this find first zero, whatever. Have you checked the object file? You mentioned that you looked usually at object files. Is it really one assembly instruction or not? Because on many CPUs, it's just one assembly instruction, and then a loop if you have more than the word size of the. But have you checked the code for that?
This particular one, no, but I think it works on par with the implementation, with the C implementation that is optimized, I believe. So it could be a good thing to check anyway. So thank you.
All right.
Right. Thank you.
Thanks.
Thank you very much.
Welcome.